Hi guys, it's Kate, and this is the first video for week 3 of Math 23B. So far we've discussed integration, exactly what it means for something to be Riemann integrable, how to evaluate Riemann integrals, and also how to set up double integrals using Fubini's theorem and being able to swap bounds whenever necessary to describe regions in the plane. Now we're going to move on to a body of functions that are a little bit more difficult to integrate using those rules. Using Fubini's theorem, we're able to basically evaluate a double integral by using an iterated integral, so effectively at any point in the process, we're only handling a single integral. And our success in being able to do that ultimately depends on our ability to take an antiderivative. But let's look at a function like this integral, the integral from a to b of 2x e to the x squared. That's great, right? We can absolutely figure out what the antiderivative is of that function, but what if it was just e to the x squared by itself? There was no 2x in front of it. When you're trying to integrate something like e to the x squared, simply coming up with an antiderivative just isn't an option. E to the x squared isn't a derivative for a function that we can just write a formula down for. And so this week's discussion kicks off with what do we do in this case? And in fact, what we need to do is go back to our definition of the Riemann integral in terms of Riemann sums. So upper and lower sums are great in theory, but generally pretty difficult to deal with in practice because they require us to be able to find the supremum and the infimum of a function over every single dyadic cube. What's great though is that we know that all of the function values over that cube will be less than or equal to the supremum and greater than or equal to the infimum, so we don't actually have to find the supremum and the infimum. If we have an integrable function, we can choose any evaluation method. That particular type of sum we'll call S sub n, and we know that S sub n is going to be greater than or equal to the lower sum. It's going to be less than or equal to the upper sum. And so for an integrable function, the lower sum and the upper sum will converge to the same limit as the level of dyadic division goes to infinity. And so by virtue of the fact that our new type of sum, which may be greater than the lower and less than the upper, as the level of dyadic division goes to infinity for an integrable function, this type of evaluation method for summing will also converge to the same limit. Let's take a look at some notions of how to use this effectively. This is pretty much how most people have had integration introduced to them, using things like the right-hand endpoint rule or the left-hand endpoint rule to approximate the area under a curve. So let's take a look at exactly how these right-hand endpoints and left-hand endpoint evaluation methods work. We're going to be talking about the right Riemann sum and the left Riemann sum. And we're just going to look at how they behave with really straightforward functions. So starting off with just f of x equals x. The right-hand Riemann sum and the left-hand Riemann sum used on a subinterval of length h are going to both make an error that's proportional to h squared. The right-hand Riemann sum is going to overestimate it. The left-hand Riemann sum is going to underestimate it. The number of subintervals in our parent interval from a to b is proportional to 1 over h. Note that 1 over h is the number of intervals of length h in an interval of length 1. So the sum of these errors is actually going to go to 0 as h goes to 0. So what's great about this is that, yes, as h goes to 0, or as our subintervals get finer and finer and finer, the error associated with the right Riemann sum or the left Riemann sum is going to disappear. What's even more interesting is their average, the trapezoidal rule, where instead of using the right-hand endpoint or left-hand endpoint, we use an average of the function values at the endpoints, is going to be exact. And the midpoint rule with this function, where instead we use one evaluation point right in the middle of the interval, that will also make no error. If we make our function a little bit more complicated, x squared, the trapezoidal rule, again, using an average of the function values at either endpoint, the trapezoidal rule used on an interval of length h makes an error that's proportional to h cubed. And the midpoint rule also makes an error that's proportional to h cubed, but that error is negative 1/2 times the error made by the trapezoidal rule. And we're going to go through all of these sort of like overestimating, underestimating, how is the error proportional in lecture on Tuesday. But let's take a look at that picture that relates the midpoint and trapezoidal rule. It's worth sort of noting exactly how to draw this so that the various magnitudes of error are a little bit clearer. So here we have some function. Here's our function x squared. Here are the endpoints of the subinterval. The best way to picture the trapezoidal rule is, of course, to make a trapezoid from the function value at one endpoint to the function value at the other endpoint. So it looks something like this. And the best way to picture the midpoint rule is, rather than draw in a rectangle that has a flat top and intersects the curve right at the midpoint function value, instead I encourage you to sort of visualize that rectangle with the flat top and then begin to rotate the line that is the flat top. So let me show you how that works. So rather than visualize the height of the midpoint rule's rectangle accordingly, it's very difficult to compare and contrast the midpoint rule to the trapezoidal rule. If you draw the trapezoid in and have the midpoint drawn like that, you can't tell which one's more accurate, you can't tell what's going on. Instead, I encourage you to rotate the midpoint rule through this point right here. And so what you instead want to see and use to visualize the midpoint rule is the following. It's going to be a line tangent to the curve at the midpoint that makes another trapezoid shape. And note that all I've done, rather than use this flat top to show the midpoint rule's rectangle over this subinterval, the amount that we've pivoted the left side down is the same amount that we've pivoted the right side up. And of course, this triangle right here and this triangle right here are the same in area. So we haven't changed the overall area of the rectangle that represents the midpoint rule estimation. We've just made it so that it's a lot easier to picture. And so that light blue trapezoid is an overestimate, and the light purple trapezoid is going to be an underestimate. And so you can better see exactly how the error associated with the midpoint rule is going to be less than the error associated with the trapezoid rule. And also, when one's an overestimate, the other one will be an underestimate. We'll also review calculating this explicitly in class. In fact, what's really interesting is that a mixture of 2 parts midpoint rule and 1 part trapezoid rule, which will balance out this error, is going to be exact. So remarkably, Simpson's rule is going to be exact for a cubic polynomial, and we're going to talk about using this mixture of a weighted average of 2 parts midpoint and 1 part trapezoidal rule, and do a couple of examples in class. But the general algorithm for using Simpson's rule, which is this weighted average, again, the mix of the midpoint and trapezoidal rules, means that we're going to take the interval of integration, we're going to divide it into n equal subintervals, and then we want to evaluate the function at the endpoints and midpoint of each subintervals with a total of 2n plus 1 evaluation points. And then we're going to calculate a weighted average of the function values over these points. And this weighted average, these weights are selected so that they maintain that very important 2 parts midpoint, 1 part trapezoid idea. So you'll see that the midpoints are more heavily weighted than the trapezoid function value endpoints. So we have 1, then 4, then 2, 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 then 4, then 1. And you'll see that the reason that this guy, despite being an endpoint, has a weight of 2, he is the endpoint, or she, or it is the endpoint of both the first subinterval but also the beginning point of the next higher subinterval. So that's where you end up with 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. We'll be doing this in class on Tuesday, so don't worry if it's a little bit confusing here, but what you're doing is creating this weighted average of 2 parts midpoint, 1 part trapezoidal rule. Then we divide by 6n so that the weights sum to 1. That's really, again, correctly dividing by an appropriate amount so that we get that nice weighted average. And then we're going to multiply the weighted average by the length of the interval, b minus a, to get a good approximation for, and it's exact for cubics on down, but any good approximation to the integral from a to b of some function f. We'll also briefly talk about the ability to compute integrals by taking a weighted average of nicely chosen function values over the interval. And this is the idea behind Gaussian integration. And in class, we'll successfully show that if you have a particular rule that says, here's how you should weight the various function values at well-chosen evaluation points in order to give an exact answer for a particular integral, and you have these weights chosen to give exact values for the integral for a bunch of different functions, then there is going to also be a product rule for a function that is a product of those functions that is also going to be exact. We'll specifically walk through the case where you just have exact weightings for two functions to show that then you are guaranteed exact weightings for their product, but it will become apparent to you how you can then generalize to the more complicated case where perhaps you have four functions that are being multiplied together.